speaker. First speaker is Andy O'Bannon, who is a physicist at the University of Southampton. His original degree was in creative writing and not physics, but I'm reliably informed his papers are physics and not creative writing, so that's good. So he's a lecturer in applied mathematics and theoretical physics, also some creative writing. Okay, yes, he is. And he'll be talking about string theory and whether or not our universe is a hologram. So take it away, Andy.
Hey everybody, thanks for coming. So as was mentioned, I'm going to talk about my research. And I'm going to ask a question you probably never thought about before: is our universe a hologram? So if I had to summarize my research in a single sentence, it would be this. I use a tool from string theory called holography to study strongly interacting systems. And so what I'm going to do in the talk is I'm going to go through each one of these things one at a time and try and tell you what they are, briefly, why you should care, how they're related to each other. So you have some idea of what I'm doing. So I'll start with string theory. And to describe string theory, I'm going to start with the two major achievements of 20th century physics, namely quantum mechanics and Einstein's theory of relativity. So let's start with quantum mechanics. Broadly speaking, quantum mechanics describes physics at very small scales. So roughly speaking, the size of atoms and smaller. So how big is that? Well, if you take a normal object like, say, an iron skillet, let's say it's roughly 30 centimeters across. Well, we know microscopically it's made up of atoms. This is an artist's conception of an iron atom. How big is that? Well, it's about 10 to the minus 8 centimeters. And here we encounter the fact that we're going to see a lot of very small and very big numbers in this talk. And I can't assume everybody knows this notation. This is scientific notation. So I have a couple quick slides about that. So big numbers we describe like this: 10 to the power 2 is 10 times 10, that's 100. 10 to the power 3 is 10 times 10, that's 1,000, and so on. All you have to remember is the power up here tells you the number of zeros that come after the 1. And then for small numbers, we put a minus sign. So 10 to the minus 2 is 1 over 100, 0.01, and so on. So in this case, the number is telling you the number of zeros that come before the 1. Right, so back to the atoms, that's 10 to the minus 8 centimeters. That's really, really small. But as this picture suggests, atoms are made of smaller things. In particular, at the center there's a nucleus, and then orbiting the nucleus are a bunch of electrons. Now, as far as we know, the electrons are fundamental particles. What that means is that, at least at this moment in history, we have no experimental evidence that they're made of anything smaller. However, we know the nucleus is not a fundamental particle. It is made of smaller things. Well, first of all, how big is a nucleus? Well, it's about 10 to the minus 12 centimeters. So it's about 10,000 times smaller than the atom itself. And as this picture suggests, it's made up of two types of particles. They have funny names. They're called protons and neutrons. The names are not important. How big are those? Well, each one of those is about 10 to the minus 13 centimeters. We're getting smaller and smaller. And it doesn't end there. The protons and neutrons are made of even smaller things. With even weirder names, they're called quarks. And at this point, we're reaching the boundary of experiment. So I can't tell you exactly how big a quark is. I just know it's smaller than a proton or a neutron. So I know it's smaller than 10 to the minus 13 centimeters. And so as far as we know, so as far as we know, the quarks, right, the electrons in the quarks are fundamental particles. And their interactions are described by quantum mechanics. And one of the fundamental principles of quantum mechanics is the Heisenberg uncertainty principle. And nowadays, when you mention the name Heisenberg, of course, the first thing people think is Breaking Bad. But there was a real Heisenberg. He's kind of infamous because he was a German physicist, and he stayed in Nazi Germany when all the other scientists were fleeing, like Einstein. And he actually collaborated with the Nazis on their atomic bomb program. And he never lived that down. But anyway, it was important for quantum mechanics. So the Heisenberg uncertainty principle is the statement that in quantum mechanics, the more precisely a particle's position is determined, the less precisely its momentum can be determined, and vice versa. So in other words, if you have a quantum mechanical particle and you measure its position to more and more decimal places, you'll only be able to measure its momentum to fewer and fewer decimal places. You know, less and less, there's more and more uncertainty in its momentum. and vice versa. So you can never know both of them with perfect certainty. And the point of that is that as a result, quantum mechanics is what we call probabilistic. So what does that mean? Okay, well, I'm a theoretical physicist, so what I want to do is take some equations, do some calculation, and get a number that will be a prediction for an experiment. But in quantum mechanics, you don't just calculate one number. When you do a quantum mechanics calculation, you get a set of numbers that determine all the possible outcomes of the experiment. Outcome number 1, number 2, number 3. And associated with each of those is some probability, 20%, 15%, and so on. So in quantum mechanics, the prediction is not, if you do the experiment, you'll get this one number. Instead, the prediction is if you do the experiment 100 times, well, 20 times you'll get outcome number 1, 15 times you'll get outcome number 2, etc. So even though it's probabilistic, it still is predictive. You can still make predictions and check the theory. And what I really want to emphasize is that it's one of the most successful theories we have in physics. It describes an enormous number of phenomena. It describes all of electricity and magnetism, all the phenomena that are familiar, like static electricity, lightning, light bulbs, refrigerator magnets. It describes the structure of the periodic table, which of course is the basis for all of chemistry. It also describes radioactivity and nuclear physics, whether it's for nuclear energy or for nuclear weapons. And it can also describe the nuclear reactions that happen in the sun, which produce all the light and the heat that we see. But it's incomplete because quantum mechanics doesn't describe gravity. So it can describe the nuclear reactions in the sun, but not the gravitational attraction that holds the sun together. We have a different theory for that, and that's what brings me to the other achievement of 20th century physics, Einstein's theory, because that's a theory of gravity. And I don't want to go into details about that. I'm going to give you a very rough sketch of how that works. Einstein's key idea, about 100 years ago, was that you should not think of space and time as just rigid, like the points in space are just rigid and fixed. Instead, you should think of them as malleable. So you should think of space and time as a substance like Play-Doh, or silly putty, or bread dough, where it can work and deform and stretch. It can also expand, just like bread dough in the oven. And in fact, that's what our universe is doing right now, it's expanding. And then in particular, the amount of the warping is related to the amount of matter, or mass. So if you have a very big object like the sun, for example, it'll warp space a whole lot. And if you have smaller objects, they'll warp space a little less. And that's actually what determines the gravitational interactions between objects. So if you have a big object like the sun, it'll warp space a whole lot. Some smaller object comes along, like say a planet. Technically it is warping space, but not very much compared to the sun. And so that object's motion will be determined by the warping caused by the sun. And this actually is also very predictive. It's also a very successful theory, but only on much larger length scales. So in particular cases where you have really big objects with a lot of mass. So for example, what kind of scales are we talking about? Well, for example, Einstein's theory very precisely predicts the orbits of satellites around the Earth. That's about, on average, about 30,000 kilometers. Also the orbits of planets, this is an artist's conception. The orbits of planets around the sun, that's about 10 to the 9 kilometers or a billion kilometers. And even larger scales, like to say the size of a galaxy, which is about 10 to the 18 kilometers, a billion kilometers. And even bigger, up to the biggest length scale that we know, 10 to the 19 up to 10 to the 23 kilometers. So the 10 to the 19 is the average distance between galaxies. 10 to the 23 is an estimate for the size of the observable universe. And on these very large scales, Einstein's theory is very successful, and it predicts the physics, the motion of these big objects very well. But it's also incomplete because it's not quantum mechanical. So in Einstein's theory, you do just do a calculation, you get one number, and that's the prediction. And what I want to convince you is that's a problem because the real world has both quantum mechanics and gravity. And in particular, so even in an atom, even though it's very small, the quarks and the electrons, they do have mass, and they are attracting each other gravitationally. It's just very, very small because their mass is so small. And similarly, well, okay. So in principle, all of those things are happening. Quantum mechanics and gravity are happening at the same time, but we don't have any theory to describe them. Most of the time we can get away with it because you can ignore one or the other. So yes, it's true that in an atom the electrons and the quarks attract each other gravitationally, but it's so tiny you can ignore it. And similarly, any quantum mechanical effects you can usually ignore for a really big object like a galaxy. But there are cases where you have to deal with both at the same time, namely when you take a huge amount of mass and cram it into a really small space. So you have a lot of mass, so space warps a whole lot, you can't ignore gravity, but you're in a really small space, so you can't ignore quantum mechanics. And the two main examples of that are black holes. This is a new, this year, image of the first ever image of a black hole. And the Big Bang. So a black hole, if you don't know, is just you take a whole bunch of mass and you cram it into a space so small that space will actually warp so much that even light cannot escape. That's why it's called black. And then the Big Bang, as I mentioned, the universe is expanding, so just logically, if you go back in time, eventually everything will converge to a single point. So basically, you're taking everything in the universe and cramming it into a point. So there it's really obvious you can't ignore quantum mechanics or gravity. And that's really important because the whole universe comes from the Big Bang. So we really need a theory of what's called, so the two major achievements of 20th century physics give rise to the major problem of 21st century physics, how to combine the two, quantum mechanics and relativity. And a theory that has both, well, we have a name for it, it's called quantum gravity, or the theory of everything, where everything doesn't mean like economics and art history and stuff. It means everything in physics, all the physical phenomena that we observe. And I want to be perfectly clear, we don't know the theory of quantum gravity that describes our actual universe yet. It's a big open question. Many brilliant people have been working on it for the last 100 years, and they've all failed. It's really hard, but we don't know the answer. And that could be the end of the story, but that's where string theory comes in. Because string theory, it's currently our best guess for a quantum theory of gravity. So how do I explain string theory? Sorry, I keep screwing up the slides. Okay. So string theory begins with a hypothesis, a what-if question. So the question is, what if the electrons and quarks are not fundamental? What if they are actually made of something small? So again, I emphasize, we're now entering the realm of imagination. We're leaving experiments. But we're going to follow this idea and see where it goes. And in particular, in string theory, of course, the hypothesis is that these fundamental particles are actually made of smaller things called strings. So here's a picture of one little string. And of course, the first question people always ask me is, what are the strings made of? Because when you say string, people think of yarn or twine or something. Of course, that's wrong. And the point is that in string theory, the strings are supposed to be the fundamental objects. They're not supposed to be made of anything smaller. So if you ask me what are the strings of string theory made of, I'll give you the answer that my PhD supervisor gave me. They're not made of anything, they're just pure energy. They're little strands of pure energy. This is an artist's conception, if you want a picture in your head. But why do we call them strings? It's because of the way they move. Because they move pretty much, mathematically it's identical to the way, say, a violin string moves, or a guitar or a piano string. Namely, it can vibrate with different frequencies. And of course, in a musical instrument, those frequencies are the different notes that we hear. But the idea in string theory is that, well, all the fundamental particles are made of the same kind of string, but it's just vibrating at different frequencies. So that's why we see them as different particles. That's the basic idea, and actually starting from there, you can write down a bunch of equations and do a bunch of maths and go do a PhD. And what's very surprising is, and I won't go through the detail, but what you discover is that in fact string theory is a theory of quantum gravity, so it can actually describe both quantum mechanics and also relativity. So it could actually describe, for example, the gravitational attraction between electrons and quarks in an atom. And that's great. We consider that progress because that's the first solution we have of this problem of quantum gravity. But of course, there's a crucial question: is string theory right? And in physics, right means it agrees with experiments. So, in particular, can we test string theory experimentally? Does anybody know the answer? No, we can't. And there's a number of reasons why, but I'll give you the most important one. You can ask a really important question: how big did the strings of string theory have to be in order for these strings to describe quantum gravity? And again, you have to go and do a whole bunch of maths. I won't go through it. I'll just tell you the answer. It's 10, oh, you can't see it. 10 to the minus 33 centimeters. So that's 20 orders of magnitude smaller than we can currently measure experimentally. And that's why it's never been tested experimentally, and some people think it never will be, because it just seems practically impossible that you could ever get down to those short distances. So that's bad, and that could be the end of string theory, but this is where I transition into holography. Because holography gives us a whole new perspective on what string theory is, and also what it's good for. So to describe holography, we'll go back to 1997, and this guy, Juan Maldacena, he was at Harvard at the time, now he's at Princeton. And he was studying string theory, at the time, but with a new ingredient, namely, he was studying some strings moving around on a space with a boundary. So this is a crude cartoon where it's supposed to be in the back here, there's a wall, there's a hard wall. So the strings can move around, but they hit this wall, they can't go past. So the space ends at this wall, we call that the boundary of the space. Okay, so I'm going to tell you what holography is, and it'll sound really weird and confusing, and then I'll try to explain it. So let me just state it first. What he discovered was that this system of strings is actually equivalent to a system of quantum mechanical particles that interact with each other but not with any gravity, but living in one lower dimension. So for example, if the strings are moving in 3 dimensions, x, y, and z, then there's some particles here moving just in x and y. So what am I talking about? Okay, so the statement is that there are 2 different physical systems. And they have 2 sets of equations. There's one set of equations that describes these strings moving around on the space with the boundary. Another set of equations that describes these particles moving in one lower dimension. And Maldacena's discovery, or his statement, was that even though they look very different, they're secretly equivalent. So you can actually translate from one to the other. It takes some work to translate, and that's why it took a long time to discover this. So I'm going to try and give you some intuition for how this works. The way it actually works is it really appears that these particles are living at the boundary. And what does that mean? Well, so for example, if one of these strings is moving in some direction with some momentum, subject to Heisenberg uncertainty, but that's not important right now. Well, what happens in the system of particles? Well, what you'll see is a little cluster of these particles, and they're all together, but they're moving in the same direction with the same momentum as the string. So that's how the particles encode the information about the string. But of course, the string can move in one extra dimension away from the boundary, which the particles can't do. So how do the particles know about that? Well, if the string does move away, this cluster will start to spread out. And vice versa. If the string moves towards the boundary, they'll start to cluster closer and closer together. So the particles actually do know about information in the extra direction. And in particular, the intuition we usually have for this is that it's as though you're shining a torch on the string and it's casting a shadow on the boundary, and the shadow is sort of made by these particles. So why is it called holography? Well, okay, most of you in your wallet, you probably have a credit card. Every credit card has a hologram on it of a bird. And of course, that's because holograms are very difficult to counterfeit. But what is a hologram? Well, it's a 2-dimensional or flat image that contains enough information to reconstruct a 3-dimensional object. So a hologram actually contains, well, of course, information about the width and height of the bird, but there's also information about the depth. So you could, in principle, reconstruct the whole thing. And the idea is that's what's happening here, that these quantum mechanical particles actually encode all the information that's happening in the string theory. And so, in fact, we usually say they are the hologram of the string theory. And in fact, some people have elevated this to a principle, namely these guys, Susskind and 't Hooft. 't Hooft is a Nobel Prize winner, but not for this, but for other stuff. And the principle is the idea that just any theory of quantum gravity is holographic. It doesn't have to be a string theory. Their proposal was it's just a fundamental property, just fundamentally something that happens when you combine quantum mechanics and gravity, that you'll always be able to describe it with some lower dimensional set of equations. What I want to emphasize is that this is a really deep and profound statement. It's telling us that somehow quantum gravity is easier than we think. It's actually equivalent to just some quantum mechanics that we already know. But it's not so easy to translate. And that's one of the key questions. Like, how does it actually work? What's the dictionary to go from one set of equations to the other? And then also some other really big questions like, well, if all this is true, then does our universe have a hologram? We believe some kind of quantum gravity exists in our universe. Does that mean that literally out at the edge of the universe there are some quantum mechanical particles that somehow know about everything happening in the universe? Conversely, we have quantum mechanics. Is that a hologram of some weird quantum gravity theory that lives in one higher dimension? And the really big question, can we test any of this experimentally? That's really hard. And actually, I'm not going to answer any of these questions, because now we've reached the limits of our understanding. These are all open questions and subjects of active research right now. The last thing I want to get to is, what does all this have to do with strongly interacting systems? So I'm going to describe what those are. I'm going to build up to it in stages. So forget about all the fancy stuff, quantum gravity and string theory and all that junk. Consider a really simple system that we give to high school students. Particles in a box. So I have a box, I have some particles floating around inside, and when they hit the walls of the box, they bounce off and keep going. So they're stuck inside. All right, so the simplest thing we know how to do is a non-interacting system. So that's when the particles don't interact at all. What does that mean? Well, that means that if two of them approach each other, well, if they don't interact, they will literally just pass through each other and keep going, with no change in their direction or their momentum. And this is important because this is completely under control. We know how to write down the equations, we know how to solve them. We can tell you anything you want to know about this system. So if you have a box of these particles, we can tell you the temperature, the pressure, anything else you want to know. But it's boring because nothing ever changes, and it doesn't actually describe any real system. Real systems have interactions. We can turn on some weak interactions. What that means is now, as two of the particles approach each other, they'll give each other either a very weak push or a very weak pull, depending on whether the interactions are repulsive or attractive. But it's very weak, and so in particular, they will each experience only a very slight deflection. And this case is mostly under control. We know how to write down the equations. We don't know how to solve them exactly, but have very good approximation techniques. And it's considered essentially a solved problem. But that brings me to strongly interacting systems where, obviously now, when the two particles approach each other, they give each other a really violent kick. And so their direction, or their trajectory, can experience dramatic changes like this. And, well, to make a long story short, this is not under control at all. We know how to write down the equations, we have no idea how to solve them. And it's not just theoretical, because there are real systems that are strongly interacting. And some of those systems have remarkable properties that might have revolutionary applications. So I've just listed a few of them here. I won't go into details, I'll just give you some names. There's high temperature superconductors, that's a picture of one. These could be, they can dramatically improve energy efficiency, for example, in power lines. There's things called topological insulators, here's a picture of some. This could be a basis for a new generation of quantum computers called quantum computers. And then there's graphene. That's just a single sheet of carbon atoms arranged in a honeycomb lattice. It's very, very special. It's extremely strong. It's a very good conductor. And it could be the basis for a new generation of electronics. And actually, this is a proposal. Using graphene, you could, in principle, make something like an iPad, but it's as thin as a sheet of paper and transparent. I don't know why you would want to do that, but you could. And it hasn't been done yet, I should emphasize. The point is that all of these, they have remarkable properties, but they all involve strongly interacting particles at the quantum mechanical level. So we really have no idea where their remarkable properties come from microscopically. Okay, that's the real world. These are all real systems. But what does it have to do with holography? So back to my string theory and my quantum particles at this boundary. What I didn't tell you was that when these particles are strongly interacting in the sense that I described, the string theory is actually weakly interacting. That's part of the dictionary that we've learned. And so this is useful. So even though we don't entirely understand holography, where it comes from, we can still use it. We know it exists, and we can still use it. So in particular, what I do in my research is the following. I go to these real strongly interacting systems that we want to study. I formulate some question. I go to my holography. I can translate that question to the string theory. And on the string theory, I can do the calculation because they're weakly interacting. And then I get some results, and I can translate that. And so in that way, I can use holography to answer questions about these real systems. And the upshot of all that is that, as I mentioned, this is a totally different perspective on what string theory is and what it's good for. I'm not talking about quantum gravity here. I'm just talking about these real-world things. Right, so hopefully now, when I say what my research is about, you have some idea of what I'm talking about. I use a tool from string theory called holography to study strongly interacting systems. And the real message I want to leave you with is that if somebody asks you what is string theory good for, there's actually two answers. One is that it's our leading candidate for a theory of quantum gravity. But there's another one, that it's a useful tool for studying strongly interacting systems because of holography. And I emphasize this because the public usually just hears the first answer. But in fact, in the string theory community, almost nobody is working on that anymore. Almost everybody is working on the second one. And that includes people right here in Southampton. So in fact, at the University of Southampton, there's a group of a dozen people, including myself, who are working on various aspects of holography, including all the questions that I mentioned before. You might see us walking around town somewhere. So I encourage you to bother all of them with your questions. Anyway, I'm done, so thank you very much.
Does anyone have any? That's not it. Does anyone have any questions for Andy? Yes, yeah.
Yeah, with the Heisenberg uncertainty principle, would you say it's analogous to like taking a photograph with a different shutter speed? So if you use a really fast shutter speed, it freezes the movement, and you can see the position, but you don't know what its momentum was. If you use a slower shutter speed, it's blurred. You can tell how fast it was moving, but you don't know exactly where it is.
Yeah, it's analogous. I would say it's analogous, and it might even be even mathematically very similar, if not identical. Anybody's familiar with math? It's actually just a property of Fourier transform. Anyway.
What is it about macroscopic objects that why don't they become quantum mechanical? Why is there this coherence for macroscopic objects? What happens to the observer say?
Yeah, I'll repeat it, you can tell me if it's right. So, why don't macroscopic objects behave quantum mechanically? I was a little fast and loose. There can be some macroscopic objects that exhibit quantum behavior. It has to do more with the wavelength of the object and how big it is compared to the size of your system. But in general, it's not really a statement about measurement or decoherence. It's really just a statement about you don't start to see the probabilistic effects until things are confined in a pretty small space. If you take, say, an atom and confine it in some kind of space, they do this with like lasers and stuff, you'll actually see that it starts, it doesn't look like when you think of a particle, you think of a little hard bowling ball or something, but in fact, real particles aren't like that. They're actually little lumps of probability. They're sort of fuzzy, and that's what quantum mechanics is telling you. And you only start to see it on short distances. If you took, say, a galaxy and if you crammed it into a small enough space, you would start to see that fuzziness. Wasn't a great answer.
In the formulation of string theory, how natural is it that you have quantum mechanics agreeing with gravity? So do you just quantize the string and then you naturally have this agreement between the two theories?
Yeah, I can give a little bit of history. So they wrote down the equations for the string. There's a process where you can take a system that's not quantum mechanical and sort of quantize it. So you can, in particular, impose Heisenberg uncertainty on its position and momentum. And yeah, back in the 70s, people did that with these strings. They wrote down, you start with exactly the same equations as for a violin string or something like that, but then you impose Heisenberg uncertainty. And then, like I said, there's a lot of mass, but it does fall out pretty naturally, that you do get a gravitational attraction between things. It falls out pretty much immediately. I think that's sufficient to answer your question. It's very natural in string. Any other questions?
It might be a mean question. So you're talking about using hologram studies strongly interacting systems by basically applying a dictionary to move your equations into a weakly interacting system. How do you know you're getting the dictionary right?
Oh, well, we can test lots of things. So the question was, we have this holographic dictionary, and how do you know you're getting it right? There are cases where you can calculate things independently on both sides. And they always agree. In all the cases we have so far. What we don't have, and what people would really like, is where you start with one set of equations, and that's all you have, and you somehow apply some recipe and you're able to derive the other set of equations. We have no idea how to do that. Instead, Imelda Sena just kind of stumbled upon this. But once you know it's there, yeah, then you check things on both sides. It's always passed every test, probably thousands, and at this point we trust it and everybody believes it.
Oh, yeah.
So, you said that the quantum particles are strongly interactive, but the strings are not. What if two of the quantum particles hit each other? Did it cause anything to do with the strings, or did they just go about?
Well, the strings, so point particles hitting each other is different from strings hitting each other. If the point particles hit each other in the way I described, what would happen with the strings is actually a pretty messy process. Because they aren't just points, right? They have some length. So they kind of hit each other and they can do things like break and form two new strings. And it's actually possible for them to do that in a weakly interacting way, meaning they wouldn't actually change their momentum that much. Even if the particles in the quantum theory would be strongly interacting and might experience a big deflection. So yeah, long story made short, it's because the strings are not point-length. Mathematically, it's because they have some length. And so they're big floppy objects, and so when they hit each other, pieces can break off and all kinds of weird things can happen. Yeah, so they can experience a small deflection.
Right, so I'm afraid we have no more time for questions because we're going to have a 10-minute-ish break before the next speaker at 10 to 8 to let everyone grab coffee and food and go to the loo and stuff like that. So we can all thank Andy one more time.